The true nature of fast radio bursts becomes clearer as scientists study the polarization of light. Greetings, everyone. Today we will be delving into an intriguing subject in our video. A recent publication in the Astrophysical Journal has brought forth new information regarding the origins of fast radio bursts, FRBs. By examining polarized light emitted from 128 non-repeating FRBs, researchers have made significant discoveries. These bursts have been observed to emanate from galaxies that bear resemblance to our very own Milky Way, characterized by moderate densities and magnetic fields. This study suggests that non-repeating FRBs may originate in less extreme environments when compared to the few repeating sources that have been previously examined. The findings from this research offer valuable insights into the nature and production of FRBs. Now, without any further delay, let us begin our discussion. The properties of polarized light emitted by 128 non-recurring FRBs, which have only emitted a single burst thus far, have been extensively examined in a study published in the Astrophysical Journal today. The findings indicate that these FRBs likely originate from galaxies similar to our own Milky Way, characterized by moderate densities and magnetic fields. In contrast to previous studies that have examined limited numbers of hyperactive repeating sources which seem to originate in dense and highly magnetized surroundings, the focus of research on fast radio bursts, FRBs, has expanded. It has been discovered that only a small fraction, approximately 3%, of the identified FRBs exhibit repetition, originating from a specific source that has emitted multiple bursts since its initial detection. Traditional radio telescopes have limitations in their ability to observe the sky, as they can only capture small sections at a time. This restricts their capacity to concentrate on recurring FRBs that have established positions. However, CHIME, with its unique capabilities, can conduct wide-ranging surveys of the sky, enabling it to detect both recurring and non-recurring FRBs. Lead author Ayush Pandey, a PhD student at the University of Toronto's Dunlap Institute for Astronomy and Astrophysics and the David A. Dunlap Department of Astronomy and Astrophysics, emphasizes the significance of this initial glimpse into the remaining 97%. By doing so, it prompts a re-evaluation of our understanding of fast radio bursts, FRBs, and sheds light on potential distinctions between repeating and non-repeating FRBs. Since their initial discovery in 2007, FRBs, which are bursts of intense energy emitted from far-off locations in the cosmos, have captivated scientists. Despite the documentation of more than 1,000 FRBs over the years, the precise origins and mechanisms behind these phenomena remain elusive. Additionally, researchers have been pondering whether the environments giving rise to repeating and non-repeating FRBs share any similarities. Pandey explains that they have developed a fresh approach to examining the data related to FRBs. Rather than solely focusing on the intensity of the light, they are now considering the orientation of the light's oscillating electromagnetic waves. This approach provides supplementary insights into the origins of the light, the obstacles it encountered during its vast journey spanning millions of light years, and the specific locations where it was generated. The interpretation of light as various colors is based on the wave nature of its travel, with different wavelengths determining the specific hue. A significant portion of light in the cosmos consists of wavelengths beyond human visual perception, such as those emitted by FRBs. However, radio telescopes like CHIME have the capability to detect and observe these unseen wavelengths. Light that is polarized consists of waves that oscillate in a solitary plane, whether it be vertical, horizontal, or any angle in between. The polarization of light emitted by FRBs has been observed to undergo two distinct variations, over time and in relation to the color of the light. These alterations provide insight into the potential origin of an FRB and the substances it encounters during its voyage to our planet. By examining the variations in the polarization direction across different light wavelengths, valuable insights can be gained regarding the density of the region where a fast radio burst, FRB, originates and the level of magnetism that exists within it. In order to comprehend the nature and production of FRBs, scientists must gain insights into the specific conditions in which they occur. The findings of this research indicate that the majority of non-repeating FRBs differ from the limited number of repeating sources that have been previously examined. This suggests that the sample under investigation either belongs to a distinct population or represents more advanced iterations of the same population, originating from a comparatively less extreme environment with a reduced frequency of bursts. The Dunlap Institute at the University of Toronto, University of California, Santa Cruz, University of Amsterdam, and McGill University are among the collaborating institutions. Collaborating institutions across North America, including the University of British Columbia, McGill University, and the University of Toronto, co-lead the CHIME project. This project is situated at the Dominion Radio Astrophysical Observatory, which is operated by the National Research Council of Canada and serves as a national facility for astronomy. It is important to acknowledge that this observatory is located on the traditional, ancestral, and unceded territory of the Syilx Okanagan people. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.